So this is a problem set in lecture 2, October 2012, of a kind of weird structure which consists of just an equilateral triangle. It's got two forces applied to it, a 4 kilonewton force and a 2 kilonewton force. I think I said that the length of the sides are 2 meters each. Doesn't make it much more realistic. And we're using two symbols to show how it connects to the real world. And I guess the weird thing about this structure is that instead of it resting on the ground, it's resting on its bottom right corner on a hinge, but then the top apex is kind of hanging on a roller. So I would interpret that as being sort of held up on something which allows it to move horizontally, but not vertically. So rule number 1 is to draw a clear free body diagram, as clear as you can. Now, writing on this pad is not the most easy thing to draw very straight lines with, but I'll do my very best. So here's the structure again. It's an equilateral triangle. Okay, so you should draw that. Draw it to scale. Use a ruler if you want to. That might help you to solve it. It will certainly help with geometry. And sometimes figuring out lengths is really important when it comes to taking moments and so forth. So drawing it to scale, drawing on squared paper, all of these things help to spot helpful geometry things. So those are two applied forces. Clearly that's not all that happens. So we need to show what the outside world does to the structure, or in other words, reactions. Now a pinned joint can always apply some sort of force vertically and some sort of force horizontally. Now I'm showing it acting from right to left just because I've got a hunch, it's a very strong hunch, that that's the direction it will be acting in, because I guess I'm looking at that 2 kilonewton force pushing everything to the right, so I'm thinking the support must push back in the other direction. Doesn't matter which way you round, you show either of those forces. If you get a negative number for the value of the force later on, it just shows that it was acting actually in the other direction from what you expected. Similarly, I'm going to show the force that the roller pin support applies to the structure as a single vertical force. Okay, so it can't apply any force in this direction. Okay, that isn't there, can't be there. Okay, so that's my free body diagram. 3 forces I don't know. There's always 3 forces we can work out using equilibrium conditions. So let's give them names. I'm going to be a bit unadventurous. I'll call this one F1, F2 and F3. So the trick always is to try and figure out the quickest way, the most convenient way of calculating those forces. If it's quick, it saves you time and less chance of making a mistake. Okay, I've just almost without thinking about it, I'm drawing in the line of action of F3 there. Never a bad thing to do, line of actions. Okay, whenever you see the forces, and what I would want you to do with a system like this is not see the structure at all, not think about internal forces in the structure, but just see 5 arrows acting on something. Doesn't matter what that something is, and they're in equilibrium with each other. So this ceases to be a structural engineering problem and it becomes a simple plane statics problem, to use the jargon. Okay, so how are we going to work out F1, F2 and F3? Well, I can see straight away, and I'll say it more formally than I did before. I'm going to use the fact that the net horizontal force equals 0. Now this is just my own shorthand. You're welcome to use the same. So that's the sum of the horizontal forces is 0. I need to say what I'm doing. That's really important. If somebody's coming along and checking it afterwards, they need to know what you're doing. So looking at what horizontal forces there are, I can see the only things with a horizontal component are F2 and the 2 kilonewton force, and one is equal to the other. So effectively I've put on one side of the equation forces acting to the right, on the other side forces acting to the left. Simple. Now F3 and F1, well, you might be tempted to take moments about, sorry, you might be tempted to, give me the answer away there, you might be tempted to resolve vertically. I mean, that would be fine. You would find that f1 plus 4 equals f3, which is completely true, but then you'd still be needing to find another equation to give you more information to calculate either f1 or f3. So my advice would be, why not just go straight to an equation that gives one of those forces? And an obvious point to choose, let's label the vertices A, B and C. Okay, these aren't the only points we need to consider taking moments about. That point down here might be a good one as well. Oops. Okay, so I have a quick look at that and I think to myself, well, I think C looks like a nice point with two of the unknowns go through that. So I'm going to consider moment equilibrium about C. Okay, that's my shorthand. That just tells me what I'm doing. It's not part of the equation, it's just to help the reader. Okay, so clear diagrams, descriptions, all help the reader. Okay, also good for exams, of course, because the reader needs all the help he can get. So let's look at C. What moments are there about C? Well, I can see 4 kilonewtons, which is tending to act clockwise about C, with a lever arm of 2 meters. I can see that straight away. I can see 2 kilonewtons. Here's its line of action, all along here, all along here. So remember, we're considering this point down here, C. So we're needing to find this distance here. So that's the distance from C to the line of action of the 2 kilonewton force. Okay, and that has a value of 2 sine 60, or 2 cos 30. Okay, and I know that sine 60 is root 3 over 2. I'll calculate that in a minute. So that's what the value is, and that's a clockwise moment as well. And finally, the only other force that causes a moment about C is F3. I've drawn its line of action already, and the perpendicular distance from C to that line of action runs along the bottom of the triangle here. You can see that. So you can see the lever arm there is 1 meter. Okay, I've just calculated this on my calculator. That's equal to 1.73, which seems about right. Okay, so moments about C now. We've got 4 times 2 plus 2 times by 1.73 equals F3. Can't draw that for some reason. I'll try again. Times by 1. So therefore F3 equals, I'll quickly calculate that, hopefully 11.46 kilonewtons. Okay, so now I know F3. So next step would be, I could resolve vertically now that I know F3, or I could take moments about, where would be a good point? I could take moments about anywhere to find the right answer, but a good spot would be to take moments about D. Let's do that, because getting the hang of taking moments is a good thing. So we're taking moments about D. So what have we got there? F2 doesn't cause a moment, F3 doesn't cause a moment, F4, so 4 kilonewtons causes a moment of 1 clockwise, 2 kilonewtons causes a moment of 2 sine 60 again, clockwise, and F1 acts at a distance of 1 meter anti-clockwise. So we can see that F1 is equal to 7.46 kilonewtons. And that looks about right, because just in our heads resolving vertically, we've got f1 plus 4 equals f3, and clearly that's worked out to be the same. So that would be a check, actually. If we were uncertain about our calculations, we could use yet another equilibrium condition. So we could take moments at another point, or we could resolve vertically. If that equation works out, and that's a good indication that our other sums are right.